Hello, my name is Ivory Shriphorn, and this is my presentation for Module 3. So the graph centralities that we are focusing on are stress, betweenness, closeness, and graph. Stress centrality is defined as the centrality of a focal vertex Z. That is the total number of shortest paths in the graph that includes C. So from two vertices, preferably X and Y, and a focal vertex Z, and the total number of shortest paths from X to Y that includes Z. Betweenness centrality is the centrality of a focal vertex Z that measures a proportion of shortest paths which pass through Z. Closeness centrality measures how close a focal vertex Z is to each other vertex in the graph. And graph centrality measures how close a focal vertex Z is to the most distant vertex in the graph. So a real-world example for stress centrality includes if you had to take the bus home from work and you needed to stop somewhere. So first, the equation for stress centrality is S of Z equals sum of f of x, y, z for all vertices that are not equal to, x is not equal to y, which is not equal to z in all vertices. And the f of x, y, z represents the number of shortest paths from vertice x to y that include z. So for example, say you have to ride the bus home from work, and luckily for you, despite the different proportions of the lines, that to each stop from the bus, on the bus, is exactly the same length or exactly the same time from each other. So you want to go home. You're at work and you're wanting to go home, but you need to stop at Kroger because you need to get groceries. And you want to know how many of the shortest paths you can take to get to Kroger to get home. Because you need to go to Kroger, you need to get groceries. So looking at this graph here, actually there's only one shortest path, and keyword shortest path, because there are other paths that include Kroger. For example, work to Starbucks to bank to Kroger to home, or work the post office, Kroger to home. But we're looking for only the shortest path that includes Kroger, and there's only one, and that is from work to the post office to Kroger to home. So the answer is 1 for the stress centrality. The closeness centrality in the real world is similar to, the graph is similar to the one in the previous slide. But first, the equation for closeness centrality is C of Z equals 1 over the sum of D of Z V for all vertices V and V. So essentially, D ZV are the shortest paths from V to Z. So any vertex, Z to every other vertex in the graph. The sum of those and 1 over the sum of those. So say you're looking to buy a home in this example, and you want to know how close this home is to all your other places of activities in your life. So we have work, Starbucks, the bank, your kid's school, and the post office. And so we want to know the closeness centrality of this home here compared to, with all of these other places of activities. So first, and they're all the same length from each other. It's an unweighted graph. So they're all the same length, length away from each other, same time away from each other. So from home to the bank is 1, because there's one line. from home to your kid's school is 1, because there's 1 line. Home to the post office is 1, because there's 1 line. These are all the shortest links, remember? And then home to work is 2. 1, 2. This is the shortest, because you can go from the bank to Starbucks to work, but that's not the shortest, so we're going to ignore it. And then from Starbucks, it's both ways. You can go from the bank to Starbucks. Oh, I'm sorry, no, that is the way. You have to go from the bank to Starbucks, which is only 2. So if you add all those together, it's 1/7. So that's the closeness centrality of home to every other place of activity in your life. Comparatively, say you want a house that was closer to your work, and say the library is where close to this home. So say you want to compare your work or this house near your work to these other places of activities, just to see how close everything is. You know, if you weren't to compare homes, possible homes, a home near your work has a lower closeness centrality, because from work to post office is 1. From work to, this is now the library, because say this home is near the library, is 2. Work to the kids' school is 3. Work to the bank is 2, and work to Starbucks is 1. So that's 1/9. So not as great of a closeness centrality as this original home here. So you can use that, especially when thinking of locations for, possible maybe like a restaurant, or again, like a home, just to see how much traffic or how close things are, so you can keep in mind, what you need to keep track of. So stress centrality, and just a graph. Remember, we said stress centrality is the sum of all shortest paths and from X to Y that include focal vertex Z. So in this graph, we have vertex 1 to vertex 6, but we're going to check the stress centrality of vertex 4. So we have a few options. The first option is going from vertex 1 to vertex 2 to vertex 3 to vertex 4 to vertex 5 to vertex 6. It's the longest one we can do. That includes, actually, I think it's the longest one in general. And altogether, because this is a weighted graph, adding all of these edges together, it comes to 23, kind of high. Option 2 is from vertex 1 to vertex 4 to vertex 5, to vertex 6. And that comes out to 14. Then option 3 is vertex 1 to vertex 4 to vertex 3 to vertex 5 to vertex 6, and that comes to 12. And although that last one has 1 extra vertex in its path, it's still lower, because this 10 between vertex 4 and vertex 5 creates a longer path, a more distant path. So actually, option 3 is our answer. There's only 1 shortest path that includes vertex 4 from vertex 1 to 6. And it is the last one. It's option 3. Then betweeness centrality, same graph, but to make it slightly easier, is unweighted graph. The betweenness centrality formula is B of Z equals sum of F of X, Y, Z over Q, X, Y, for all vertices X not equal to Y not equals to Z in V. So Q of X, Y are some pairs of vertices X and Y as the number of shortest paths from X to Y. So you'll take the sum of all paths, shortest paths from X to Y that include the focal vertex Z over all shortest paths from X to Y. So, for example, we're going to do the betweenness centrality of V4. So actually, you can just ignore all the ones that go from V1, for example, to V4, or V2 to V4, V3 to V4, V5 to V4, and so on. So instead, we're going to focus on the other paths. So the first one is V1 to V2. V1 to V2 is just 1 because there's one line, it's unweighted. So that goes for the Q of XY. And because it does not include V4, there's a 0. So it's 0 over 1. Then to get to vertex 1 to vertex 3, there's 2 ways to go. You can go vertex 1, vertex 2 to vertex 3. That's successful. Or you can do vertex 1, vertex 4 to vertex 3. And because there's 2 paths available, there's a 2. And one of them include vertex 4. So this is 1/2. So from vertex 1 to vertex 5, the shortest one actually has to include vertex 4. So this is 1 over 1. The same thing from vertex 1 to vertex 6. The shortest one has to include vertex 4, so it's 1 over 1. Then from vertex 2 to 3, it does not include V4, and there's only 1, so it's 0 over 1. From V2 to V5, there's only one shortest path and does not include V4, so it's 0 over 1. V2 to V6, again, there's only one shortest path, so and it does not include vertex 4, so it's 0 over 1. Same for V3 to V5, V3 to V6, and V5 to V6. So if we add all these together, because it's a sum, 1 over 1 plus 1 over 1 plus 1 over 2 is 2.5. So V4 has betweenness centrality of 2.5. Now closeness centrality, we talked about this a little bit already, but again, the formula is C of Z equals 1 over the sum of D of ZV. Remember, so D of XY is the shortest, the length of the shortest paths from X to Y. So this is the length of the shortest path from Z, focal vertex Z, to all other vertexes. And we will add those all together, and 1 divided by that sum. So possible that paths are vertex 1 to vertex 4. 1 is the shortest distance. From vertex 2 to vertex 4, 2 is the shortest distance on both sides. 1, 2, 1, 2. Vertex 3 to vertex 4 is 1. Vertex 5 to vertex 4 is 1. And vertex 6 to vertex 4 is 2, because the shortest distance is 1, 2. So we add all those together, and the closeness centrality becomes 1 over 7. The graph centrality, remember, is the max distance that a focal vertex is from another vertex. So G of Z equals 1 over the max of D of ZV. And remember, D of ZV is the shortest path from focal vertex Z to all other vertices. Then we're finding the maximum of all of those. So again, the possible paths from, and this one's weighted, so it'll be slightly different than if it was unweighted. But from vertex 1 to vertex 4, it's just 1 because there's a weight of 1 at this edge. From vertex 2 to vertex 4, it's 3 because 2 to vertex 1. So this is amount 2. And then vertex 1 to vertex 4 is 1, so there's 3. Vertex 3 to vertex 4, the shortest length is this 3 right here because it's direct. Vertex 5 to vertex 4, upon looking at it, if this was unweighted, would just be this one line here that actually equals 10. But from vertex 5 to vertex 3 to vertex 4 comes out to 8. This is technically shorter because its value is slightly lower. So this is the shortest path. Then from vertex 6 to vertex 4 is very similar. You would think you would come direct from vertex 5 to vertex 4, but however, this comes out to 13. So if you go from vertex 4 to 5 to 3, vertex 6 to 5 to 3 to 4, that's 11, which is a shorter length. So because 11 is the max one from V6 to V4, that is the max of all of their numbers, all of their comparisons. V4 has a graph centrality of 1/11. So this is a pseudocode that I found for betweenness centrality. It is not mine. It has been used by other universities and other textbooks. I'm going to try to explain it the best way I can. It was written by a man named Brandis. And it's about the betweenness centrality, shortest path centrality. And it uses some aspects of dynamic programming because it uses some calculations of other betweenness centralities to find another betweenness centrality of another node, and so on. So let's start with the input. The input obviously is graph with the vertices and edges. The data is a Q, which is Q, and the stack, which is S, which are both initially empty. And for all vertices in the set of vertices, the distance of a vertice is the distance from the source. So the source is the vertice that was before it. So example, this V right here, its source is S. This source for W is V. So it's the one that comes before it. Pred of V is a list of predecessors on shortest path from source. So the predecessor of this V is S. This predecessor of this W is V. This represents the number of shortest paths from the source to all vertices. So the shortest path from S to V or V to W, and this is dependency of the source of vertice of a vertice. So this is a mathematical equation to help with the dynamic programming of if you calculate the node that is after its predecessor can be calculated, betweenness of the predecessor can be calculated from calculating the post node. And then your output will be this CBV, which essentially is here, this sum of what we were taught, the sum of f of x, y, z over q, x, y. Just a different way to write it. So for the vertice S of the group of vertices do, and this is a single source shortest path problem, it'll initialize it by for all W's, which is all the vertexes after a specific, like a focal vertex. So say V is the focal vertex. So all W's will be put into this pred W, predecessor of W. Right now it's empty. For T, which is the N, because it goes the vertex, the path is from S to T. The distance will be infinity, so positive number. And then the shortest path to T will be 0. The distance from S, the starting point, will be 0, and the shortest path of S will be 1. And then we will put NQS into this Q array. So while Q is not empty, we will deq this S and assign it to V. And we'll put this V on top of this S, which is the stack. So these are two different arrays. So again, it'll take the initial one, it'll take this S, and it'll be called V in this case. And it'll put V on the stack. And then for for each vertex that's attached to it, so again, we're starting here with S. For each vertex that's attached to it, V, so 1, 2, 3, it will check if it's found it for the first time. So if the distance of W, all vertices that are attached to the initial vertice are equal to infinity, so a positive number, then the distance of W will be the distance of V plus 1. So right now S is 0. So this next one, which is W in this case, but will be 0 plus 1. So it's 1. So this is also a W. So 0 plus 1, 1. 0 plus 1, 1. And then we will put these W's connecting vertices, the next vertices, into the Q array. And then we'll do finding the shortest edge from V to W. So if the distance from W, which is one of these three in this case, because we start with S, one of these three, is indeed the distance from V, the source, plus 1, which we have agreed they are, then the new shortest length is the length of V, which is 0. Sorry, the shortest path, sorry, and then plus the shortest paths of these three. So this will be 1. And then you'll append the source to the predecessor of these W's. So after it goes through all of the nodes in the graph, all the way down until T, it ends at T, you do this accumulation. So for all vertices in V, we will find the dependency source of V. So while the stack S is not empty, we will pop W. We'll pop the last element off of S and assign it to W. And then for the vertice that's a predecessor to W, because it's in this pred W array, we will assign the dependency source as a dependency source of V plus the shortest length of V over shortest length of W times 1 plus the dependency of W. So this is how the dynamic programming comes in, where we keep all of the amounts of dependency, or sorry, of betweenness, excuse me, from one node to its predecessor. So we find the dependency value of W, and we can use that to calculate the value, the dependency value of V, and so on and so forth. And while W does not equal S, so it's not at the start point, then the CBW, like I said before, is this sum of F of X, Y, Z over Q, X, Y, is of W is now assigned the same plus the dependency of W's. So again, so this will just keep looping through until we finally end here at the source, and it will tell us the betweenness centrality. Here are my sources on that. It has a space complexity of big O over N plus M, and a time complexity of big O of N times N plus N times 2 log N. Yes, time complexity. So finally, we have the proof of a vertex having both max stress and max betweenness. So before we were looking at V4, but right now we're going to check V2. So from V1 to V4, this is our X and this is our Y, and our focal vertex is V2. So it has a max stress of 1 because there's only one path from V1 to V4 that includes V2. It's from V1, V2 to V4. And it has a max betweenness of 1/2. because from V1 to V3 is 1. It's an unweighted graph, so it's just 1. And V3 to V4 is also just 1. But both of these don't include V2, so this would be 0 over 1, which equals 0. And this will also be 0 over 1, which equals 0. And then from V1 to V4, there's 2 ways to go. So because one of the ways includes V2, V1, V2, V4, it is 1 over the 2 possible paths, which is this 1 over 2. So because of how these nodes are connected and the amount of nodes, and they're unweighted, actually all of these nodes have both max stress and max betweenness. No one is higher or lower than the other. So it is possible for one vertex to have both max stress and max betweenness. I just found it if all vertices also had max stress and max betweenness for it to be possible. Yes, so thank you for listening to my presentation. If you have any questions, please let me know, and I hope you guys have a great day.